Hello and welcome to the QuICS Podcast, brought to you by Classiq, the quantum algorithm design company. My name is Yuval, and my guest today is Nicole Yunger Halpern, a NIST physicist and adjunct assistant professor at the University of Maryland. Nicole is also the author of a new book, Quantum Steampunk, the Physics of Yesterday's Tomorrow. Nicole and I discuss her book, Quantum Thermodynamics, whether being a woman helped or hurt her career, and much more. We hope you enjoyed this episode. Please let us know how we did by emailing hello@classiq.io. That's hello@classiq.io. Hello, Nicole, and thanks for joining me today.
Thanks so much for having me on the podcast.
So, who are you and what do you do?
I am a theoretical physicist. I wear many hats. I'm currently employed by the National Institute of Standards and Technology. I'm a fellow at QuICS, the Joint Center for Quantum Information and Computer Science, that is jointly held by NIST and the University of Maryland, where I am an adjunct assistant professor. But really the most important part of that is theoretical physicist, and also now I am an author of a book being published this spring. So I do quantum thermodynamics and quantum information theory. So the idea behind quantum thermodynamics is that thermodynamics, the science of energy, was developed during the 1800s, which was rather a long time ago, before people knew about quantum theory, before everyone even accepted that the materials of which our everyday world are made consist of atoms too small to see. So thermodynamics was built for large classical systems, and some of the concepts in thermodynamics have made their way into the quantum realm through quantum statistical mechanics, but statistical mechanics has a very different flavor from thermodynamics. Thermodynamics is an operational theory similar to information theory. When we do information theory or think about information processing, we're thinking about agents who have certain resources and want to accomplish certain tasks. We often think about an Alice and a Bob who are trying to communicate over a noisy channel, and we ask how efficiently can they perform this task. Similarly, in thermodynamics, we think about agents who want to power factories or power cars or charge batteries. And nowadays, the technology that we have is, in some ways, a lot of the technology is very different from the technology of the founding of thermodynamics. Thermodynamics was developed during the Industrial Revolution, when the steam engine was one of the newest technologies. So we need to reformulate or re-envision thermodynamics for small systems, quantum systems, information processing systems, and far from equilibrium systems. So my group and I participate in this re-envisioning of thermodynamics to create a theory of quantum thermodynamics using the mathematical and conceptual tools of quantum information theory. And we also take this toolkits of quantum information theoretic thermodynamics and take it around to different spheres of science like chemistry, condensed matter, and atomic, molecular, and optical physics, and use these tools to try to find new solutions to old problems or find new questions to ask.
So, you have a new book out, so please tell me about it.
Sure. This is called Quantum Steampunk, the Physics of Yesterday's Tomorrow. And the basic idea is that a genre of science fiction called steampunk, which I'll explain, is coming to life at the intersection of quantum physics, information theory, and thermodynamics. Steampunk is a genre of literature, art, and film. And in steampunk works, one has settings from the 1800s, so Victorian London or the Wild Wild West, settings like these, together with futuristic technologies such as time machines or automata, which are often powered by steam. So there's this wonderful blend of the old and the new that creates a sense of nostalgia and also adventure and romance. And I see this genre as really being realized in the spirit of quantum thermodynamics. As I mentioned, quantum thermodynamics was developed during the Industrial Revolution, which took place during the Victorian era. And on the other hand, quantum information is cutting edge technology. Quantum computers are still, to some extent, futuristic technologies. And so quantum thermodynamics is this blend of the old from the Victorian era and the new cutting edge in the future.
So I read the book and I found it to be sometimes whimsical and sometimes fascinating, but at all times enjoyable.
I appreciate it.
But I'm wondering if I'm the target audience. Who would you like to see reading this book?
I would love to see this book in the hands of a wide variety of people, people who are broadly educated and interested. These people might be interested in science and physics. Maybe they read the latest Brian Greene book and have maybe encountered Stephen Hawking's work on black holes. And so they like keeping up on science through, say, the news media. Or this person might be more literary, or maybe even a fan of science fiction. Or this person might be an ordinary scientist who has maybe heard that there's a lot of buzz about quantum thermodynamics and quantum computing and wants to know what all the fuss is about. But I hope that all these readers, potential readers from different backgrounds, will at least find the book fun in some way. I think that different people will get different things out of the book. It does have these very different, or it does combine different perspectives. There is hard science, but there's also a sense of aesthetics, and I make a lot of references to literature, art, and history. So I hope that these combine in a way to make the book fun in a way for everybody.
What's going to be the sequel? What's the next book in the series?
I guess we'll see where my research goes in the next decade. But I have been asked whether, since I've written a nonfiction book about steampunk, will I next write a steampunk novel? And I don't have plans to write a novel about steampunk, but if any literary agents who deal with steampunk novels or fantasy novels happen to think it would be a good idea for me to try to write one, then I would be interested in hearing from them.
Well, we should talk about the movie, of course, right? The steampunk, quantum steampunk movie. Um, in the book, you also describe bits and pieces about your journey into the field, whether the postdoc or what you learned in school and some of the people that influenced you. Um, who made the biggest contribution to who you are today?
I would like to say that I did. I'm certain that my mother would say that she did. So I'm grateful for a lot of influences on my life. I've been very grateful to have a lot of mentors across fields and across the globe, and I am very grateful to my family for its strong support throughout my life and investing in me the importance of education. And also, as I mentioned at the end of the book in the acknowledgments, my husband supports me by has supported me in particular this book by making baking muffins on weekends to support my weekend morning writing sessions. But that aside, I've been grateful for a lot of mentorship, and I think that that's particularly important for a young scientist. Science is really tough, and it's very important for us to have people who say, even if you think that what you're doing, even if you feel that what you're doing is very difficult and maybe you think that you can't make it, I actually know that you can because I have an external perspective, and here's why you can do it and why it really would be best just to stick it out because you can.
We get a lot of questions here at Classiq about diversity, and we've been fortunate to hire several wonderful women scientists. Do you feel that your path has been more difficult or maybe easier because you're a woman?
That's an interesting question. I know that there are a lot of influences that operate behind closed doors that involve diversity that I don't see. So I've been, for instance, once I attended a workshop for young women in physics who want to become faculty members at MIT. And I talked to a really fantastic physics professor at MIT who is a woman. And I asked her, sometimes I'm a little concerned, maybe I'm being asked to give talks and so on and so forth, just because I'm a woman and people want to promote diversity. And she said, don't worry about that. Just don't even think about it, because any benefit that you might actually get in this way does not even nearly counterbalance all the negative effects that you don't see that are that come your way just because you're a woman. So it's rather difficult for me to tell, but I can say that I am grateful to be in quantum information theory and quantum thermodynamics, because these fields do seem like relatively open, relatively friendly, and relatively embracing of diversity. These are in part young communities. Maybe that has to do with the reason why. There are also good support networks here. For instance, there's a Facebook group called Alice Women in Quantum Information. Alice is one of the two characters, as many listeners probably know, in very common quantum information theoretic protocols. She might be sending a message to Bob. And so this is a forum where women in quantum information gather and either share what they're proud of, or plan meetups, or just vent. And it is it's quite something to be able to express one's experiences to the group and have people in the field who are really leaders, whom one learns about in quantum computation courses, say, oh yes, I've experienced that. This is what my experience was like, and to create a sense of community.
When I started reading the book, you talk about qubits and you talk about entanglement. How does quantum thermodynamics apply, or how could it apply to building better quantum computers?
There's kind of a two-way street between quantum information and quantum thermodynamics. On the one hand, quantum computing, in part, in addition to foundational concerns, have led to the development of a wonderful mathematical and conceptual toolkit, quantum information theory. And quantum information theory is being leveraged as a toolkit to re-envision many different fields of science, such as condensed matter and high energy theory and atomic, molecular, and optical physics. So we as quantum thermodynamicists nowadays use the tools of quantum information theory, applying them to thermodynamics to envision anew how systems exchange energy and information. Then on the other hand, you can ask, might quantum thermodynamics have applications to quantum computing? So I discuss an example in the later part of the book. One example is algorithmic cooling. Suppose that we are running a quantum computer, then we need qubits that are prepared in simple fiducial states, which we often label as the zero state. And this state is often the ground state of the qubit's Hamiltonian. So in order to prepare a qubit in this state, we would want to cool the qubit to as low a temperature as possible. There are different ways to prepare qubits in this state, and one of them involves the notion of a heat bath, a large environment at some fixed temperature with which you can interact your system. There has been quite a bit of work over many years on how you can cool qubits by performing some initial gates on them to try to use the correlations between the qubits to compress the information into the qubits into just a small number of the qubits, so that some of the qubits are relatively clean and correlation free, and the other qubits hold the correlations, the entanglement, etc., so that if you look at any of them, their state looks close to the maximally mixed state, very entropic. Then you could take these qubits and the dirtier qubits and let them interact with this heat bath so that they assume the temperature of the heat bath. So they dump a little bit of their entropic dirt into the heat bath. Even though the heat bath just has some finite temperature, it doesn't have as low a temperature as you'd like for all the qubits to have. And then you repeat this process multiple times. Then you can get a lot of the qubits to an even lower temperature than the temperature of the bath. That's one example, and there are other ways that we can use quantum thermodynamic protocols to cool qubits, to reset them so that the qubits become new, good, fresh inputs for a quantum computation. So that's one example.
when people learn about quantum computers, I think one of the easily most confusing concept is the one of entanglement, which fortunately or unfortunately is fundamental to getting good quantum algorithms going. How would you explain entanglement to the uninitiated?
I think of entanglement as a relationship that two particles can share. Suppose, and this relationship manifests in correlations. So suppose that we have two particles that are entangled. We measure one particle, we measure the other particle. We get some outcomes that are a little bit random because they are, or that are random because they are measurements of quantum systems. And we can do the exact same thing in many, many trials. So prepare the particles with some entanglements, measure the particles, and obtain some outcomes. We can do this in many trials and build up many outcomes. Then we can measure the correlations between the outcomes of the measurement of particle A and the measurement of particle B. What are correlations? Two events are correlated if a change in one event tracks a change in the other event. So we can ask, to what extent do these measurement outcomes change together? And so we can measure how strongly, loosely speaking, the particles were correlated. And we can find that the correlations can be bigger than any correlations achievable with just classical particles. So if two particles are entangled, then they share a particularly strong relationship that no classical particles can share. And entanglement is a realization of the old saying that the whole is greater than the sum of its parts. Entanglement is something that isn't in one particle, it isn't in the other particle, and it isn't in the sum of the two particles that are, if they're probed individually. It's really sort of between the particles or in the joint system, not in just one plus the other individually.
Very good. Thank you for that. So you lead a lab, I think it is also called Quantum Steampunk, right? Could you
Yes.
tell us a little bit about the research that you and your coworkers are doing?
Sure. Yes, the Quantum Steampunk Laboratory is based at QuICS, what I mentioned before, the Joint Center for Quantum Information and Computer Science. I have a number of grad students and postdocs, and we are probing this intersection of quantum information and quantum thermodynamics. We approach it from a number of different perspectives. Some of our work is very abstract and theoretical, proving theorems and thinking about thought experiments. But we also run the gamut from abstract theory all the way to experimental collaborations. For instance, postdoc and some collaborators and I recently put out a paper in collaboration with Rainer Blatt's lab in Innsbruck, Austria, in which they had a set of trapped ions that were serving as qubits. They performed a certain protocol that we had proposed so that they could see a small subset of the qubits thermalized to a particularly quantum thermal state that we had predicted.
Very good. So, how can people get in touch with you to learn more about your work and about the book as well?
You can Google Nicole Quantum Steampunk, and that should bring up my group's website. The group website also has a page about the book, and you can find a link to my Twitter handle there. It's at NicoleYH11, and my email address.
Very good. Well, Nicole, thank you so much for joining me today.
Thanks so much for having me on the podcast.